So I'm going to start by going over how we can find the electron configuration of any atom and how this is going to trend to the periodic table. So you're going to be asked some questions about, what's the electron configuration of this atom or this ion, and you got to be able to just use the periodic table to be able to figure that out. So first, let's go over some notation. When we describe electrons, we're going to write them in this notation, where N is the energy level, L is the sublevel or with the type of orbital it's in, and then the number is the number of electrons. So, for example, if I'm in the first energy level and the s orbital, and there's 2 electrons, I'd write that as 1s2, or I could be in the second energy level in the p orbital. It has 6 electrons. So that's just the notation we're going to use to describe the orbitals, just to point that out first. Okay, so if we come over to our Bohr model of the atom, we know that electrons are going to want to be as close. They're going to want to be as close to the nucleus as possible. So say we just have 1 electron, it's going to be in that first energy level as far in as it possibly can, not out here at the third energy level, because that first energy level is lower energy, it's more stable. And through this, we can essentially predict exactly how the electrons are going to fill up and what order they're going to fill up in. So they're going to fill up in this order down here, and not horizontally, but diagonally. So first you will get 2 electrons in the 1s orbital, and then you will get 2 in the 2s, and then you will go into 2p6, and then into 3s2, and it goes diagonally. If that doesn't make sense, so say I have 2 electrons in my atom. Those 2 electrons are going to be in 1s2. If I have 4, 2 of them will be in 1s2, and then 2 of them will be in 2s2. If I have 8, if I'm neon, if I have 8, I could have 2 in 1s2, 2 in 2s2, and then the other 6 would be in 2p6. And that could get, 10 electrons. That could get me to 10 electrons. So you essentially just go down diagonally, and you can figure out until when you stop and just fill it up. Let me real quick give an example of this. So say I have carbon. I know carbon has 6 electrons. I know carbon has 6. Oops, on the eraser. I know carbon has 6 electrons. I know it's going to fill up diagonally like this. So if I just start writing out the configuration for this is going to be 1s2. Now I have 4 electrons left. 2s2. Now I have 2 electrons left. 2p2. And then that would be the ground state configuration for a carbon atom. So this is the first method I'm going to propose, that you can use essentially just this knowledge of writing out the rows and then going diagonal to fill up. And that's the first way you can do it. And I think this chunk, this little knowledge right here, is pretty easy to remember. You obviously just go down energy levels and then go across the type orbital from S to P to D to F. And then you just got to remember you fill up diagonally. That's the first way I would say to do it. Now, if we're just looking at the periodic table, you can also kind of just recognize what is filling up when. So we know as you go from like this element into this element, you're adding a proton. And assuming the atom is neutral, you also add an electron. So essentially, hydrogen, this first atom has 1 electron, this one has 2, this one has 3, 4, 5, 6, 7, 8, 9, 10. You essentially know how many electrons each one of these positions have. So, that might be a problem. Oh, there we go. Okay. You know how many electrons each one of these ground state atoms would have. And if you know by pattern what orbital they're going to fill up, you can very quickly figure it out. So let me just show you what I mean. I know this top spot, you're filling up the 1s orbital. This left-hand side is the 2s, and then this is 2p, 3s, 3p, 3d, 4s, 4p. Okay, now I'm looking at the sheet, but this is just going to keep going down. Let's see, 5p. Right, so if I know if I know this, I can essentially just look at the periodic table and figure out what the configuration of it is. Because when I write this out, I mean, this is the last orbital that's being filled up. So for example, let me go back to carbon. So this one's 2p. I know that this right here is where carbon is. It has 6 protons, 6 electrons in the ground state. I know that 2p is the last orbital being filled up. So if I started writing out this electron configuration, I know that everything before 2p is already filled up. So it already has 1s2, 2s2, and now 2p is being filled up. Right? And it's in the second position in this row, so it has 2 more electrons, so therefore it would be 2p2. So say, let's give another example. I don't know what element, actually, let me see. I think aluminum is this one, I believe. Okay, well, let's just pick some random element here. If I'm in 4D, I know this is 10 spots. You know, this is like 1, 2, 3, etc., etc. Let's say this is 7. I could say now of this unknown element, it's 1s2, 2s2, 2p6, and I'm just going to keep reading from left to right. So now I just finished 2p6. Now I'm going to go over here, 3s2, 3p6, and now I'm on this row, 4s2, 3d10, 4p6. Now I'm onto the row it's on. I'm then going to fill up, let me move this over a little bit. So I'm just reading left to right of all these blocks that I know. So now I'm on this row. I'm on the row that it's on. I'm going to fill up 5s2, and then I'm going to fill up 7 electrons in the 4d orbital. So 4d7. So for whatever this 7th element in the 4d row is, I would just add those 7 electrons into that last orbital that's filling up. So if I know what all these are, and I can clean it up, but I can essentially just read left to right and get the electron configuration, because I know it'll fill up, left to right. 1s is going to get filled, and then 2s, and then 2p, and then 3s, and then 3p, and then 4s, and then 3d, 4p. The only thing to remember here is that generally the d's are offset a little bit, right? So in the fourth row, we are only in 3d. That can get a little confusing, but this is consistent with this method, where if we just write out the entire configuration, you can see 1s is going to get filled, 2s is going to get filled, and then 2p, and then 3s, and then 3p, and then 4s, and then you go back down to 3d. So I think if you're going to just remember the orbitals of everything in this method, remember that the d's are whatever row you're in minus 1. So even though this one's in the 4th row, it's 3d. And then also the f rows are not really correlated at all, but I think it's pretty rare you'll get an element in the f block anyways. Okay, 2 other points. Valence electrons. Valence electrons are the electrons in the highest energy level in the outer shell. Say I have carbon, which we know is 1s2, 2s2, 2p2. How many valence electrons does it have? How many does it have in the outermost energy level? It has 2 plus 2, so it has 4 electrons. It is 4 valence electrons. Say I had let's do another one. Say I had nitrogen, which nitrogen is just 1 to the right of carbon. 1s2, 2s2, 2p3. And how many does it have in the highest energy level? It has 2 plus 3, so it has 5 valence electrons. Condensed shorthand configuration. Okay, so now this is so say, do you remember earlier when I said the element X, this massive string, as you know, this is pretty encumbersome to write, and it can get pretty lengthy. So we have a way of shorthanding this. So say, do I want to pick a new example? Yeah, I'll pick a new example. So say I'm going to pick a new one. But the moral of the story is they can get really long. As you get farther down this direction, they get really long and tiring to write. So we can do it much quicker. We have a method to do it much quicker. I'm going to write the electron configuration for chlorine real quick. Chlorine is element number 17, so it is 17 electrons. So if I write out the configuration for this, 1s2, 2s2, 2p6, 3s2, where is, yeah, okay, and then 3p5. Okay, and then, if you were to sum all these, 2 plus 2, 4, 10, 12, 17. So I know it did it right. It's got the right number of electrons. Say this is too long and I wanted to shorthand it. I can basically say, I can chunk together previous information. So I can just shorthand all of this info into another element. So what is of what I just circled, what is the electron configuration of what I just circled? That is neon. So I could shorthand this into essentially neon plus 3s2, 3p5, right? So these two lines I just wrote are essentially the same thing, because you're just writing the configuration of another atom and then writing what that atom is. And you're always going to use the noble gases for this. So helium, neon, argon, krypton, whatever's on the right. And then you're not going to add a plus either. So you can shorthand longer elements into this shorter notation and get rid of a lot of that earlier energy levels that are just kind of assumed. Let's take a look at the problems. 19. How many valence and core inner electrons are there in a neutral silicon atom? Let me first write out let's find silicon. Silicon is right under carbon. Let's write the configuration for this. So if we remember from before, this is going to fill 1s. Helium also fills 1s. This will be 2s. This will fill 2p. This will fill 3s, and then we're going to fill 3p. So we know 3p should be the last row and should have 2 electrons in there. So if I just start writing the electron configuration for this, I know I'm going to fill 1s first. So 1s2, 2s2, and then 2p6, 3s2, and then 3p2. Because the reason I put a 2 in 3p is because we have 2 extra electrons in this one. Aluminum would have 1, and then silicon is the second. Also, silicon has 14 protons, so in the ground state it has 14 electrons. 2 plus 2, 4 plus 6, 10, plus 2, 12, plus 2, 14. So, looks good. This is definitely the electron configuration for silicon. Now, how many valence electrons does it have? How many does it have in the highest energy level? This is the highest energy level, 2 plus 2. It has 4 valence. How many inner does it have? That's everything that's not valence. So these ones, 2 plus 2 plus 6, 10 inner. Which leaves us with answer choice C. 19C. Which one of the following is the correct condensed shorthand ground state electron configuration for a neutral titanium atom? Okay, let's find titanium. Ooh. Is it, let's see, it's right here. Okay, it has 22 protons, and if I remember from previously, we're going to fill 1s first. Helium also fills 1s, and then 2s, 2p, 3s, 3p, 4s. Now this one is going to fill 3d, and that's where we would stop. So I'm going to first, they want us to write it in like the shorthand, because they're giving us these, they're giving us krypton and argon, which are noble gases. So they want it in shorthand. I'm going to first write it in not shorthand, just to make sure we can do that. So if I start writing this out, I'm going to fill 1 S2, 2 S2, 2 P6, 3 S2, 3, 3 P6, 4 S2. And now we're onto the 3D. Titanium is the second element in that row, so it's got 2 electrons in that orbital, 3D2. Now, if I want to shorthand this, we're going to go back. So we're going to look this way, and we're going to look at argon. And argon has the electron configuration of this right here. So this is essentially argon. And we can just add on our 4s2, 3d2, which leaves us with answer choice D. So let's explain now some of the periodic trends that we can see in the periodic table. And I want you to constantly think about them in the context of this, which is Coulomb's law. You're never going to really need to use this in this class, but this is the attractive force that exists between electrons and protons, or any charged particles. But this is the relationship that's going to govern how electrons are pulled into the nucleus. And it's essentially responsible for all the trends we see. So I think instead of just trying to memorize, oh, blank property increases to the right, decreases to the left, blah, 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 I think that's a bad idea. If you can kind of remember the trends and how it correlates to this, if you just know generally how they work and the definition of the principles, if you know one, you know them all. So this is Coulomb's law, and it tells us the force of attraction, one, between the proton and the electrons, and also the repulsion between the electrons. So the main takeaway is that let's call this the chart. So okay, let me define things. This is force, this is radius, or just distance, and then Q's, K is a constant. Q's are my charge. Let's say this is the charge of like the protons or the nucleus. I'm gonna call it just the nucleus. Better, nucleus. And then let's say this is the charge of the electrons. Now, the charge of the electron is never going to change, but the charge of the nucleus does change. So let's compare oxygen and fluorine. Fluorine is one more proton. It has 9 protons compared to oxygen's 8. Therefore, it has, a slightly bigger Q1. Therefore, if it has a bigger Q1, it will have a bigger force of attraction on its electrons. And that's essentially going to be the basis, or the first basis, that is, for a lot of the trends we see. Also, the other major trend is kind of just in electron configurations. So, and I'll connect this in a second. But as things get bigger, there's a couple intuitive trends. So say I have this element. Removing removing this electron is going to be a lot harder than that electron, more or less. So there's going to be trends there we see as things get bigger. So let's take a look at the first 3 we're going to look at, which is going to be atomic radius, first ionization energy, and electron affinity. Atomic radius. The number one thing in atomic radius is which energy level are you in, which, when we look at the periodic table, increases as you go down. So here we're in, this is the p block. All these electrons, most outer electrons, are in the p orbital. What's the difference between carbon's outermost p orbital atoms and silicon's? Well, carbons are in the 2p, and silicons are in the 3p. I think it makes a lot of sense. So say this is the first energy level. This is the second. You have 8 in it. I feel rigorous enough to draw all 8. What am I at? 5, 6, 7, 8. Okay. This second energy level right here is where carbon's at. And whatever was below it, silicon, is now in this entire outer energy level. So which one's going to be bigger? Well, carbon only takes up this much space, more or less. whereas silicon has an entire another ring. So I think it's pretty intuitive to think that as you add an energy level or go down the columns, you're going to get a lot bigger. Now, what if we're moving, let me get rid of this, keep it clean. What if we're going horizontally and not down columns? So what about oxygen versus fluorine? Well, oxygen and fluorine are both occupying that second energy level. They look something like this. But if we come back over here to Coulomb's law, let's remember that fluorine has 9 protons. It has 9 positively charged protons in its nucleus, whereas oxygen only has 8. I drew a 0. Fluorine's pulling a little bit harder. Its nucleus is pulling a little bit harder, so all these electrons are just inched in a teensy little bit farther. So therefore, fluorine is a little bit smaller. So what does this look like? Now I'm going to give you the full big line that I don't think is worth memorizing. But big atoms are over here. As you go down and to the left, things get bigger. Pretty intuitive. Fluorine is, I like to use fluorine as the reference. Fluorine would be on the smaller side of things. So that's atomic radius. Also ionic radius. You run into some smaller effects with electron repulsion. So let's consider fluorine again. Let's consider a ground state fluorine versus one with an electron. This is 1s2, 2s2, 2p5. This one is 1s2, 2s2, 2p6. So we're up here again. Let's see. This is our fluorine. Okay, let's say it has say it only has the 5 in the p, so it's got 7 space. I'm talking about this one. It's got 7 valence electrons. And say it looks like this. If I add in an 8th, there will be a slight repulsion, according to Coulomb's law, between these 2 electrons, and they're going to kind of push each other away. And this 8th electron will cause all of them to kind of push each other away farther. So oh God, my arrows. Anyways, as you would add an electron to the same element, you'd get a teensy little bit bigger. Or it could be a big change. If for whatever reason I added another one into somehow you did this, you added one into the 3s1, you'd get a lot bigger because now you'd be occupying this. So that is atomic radius and ionic radius. Let's do some erasing. We're going to talk about first ionization energy next. Okay. Number 2, first ionization energy. This is the amount of energy required to take an electron away. Conceptually, how hard is the atom holding on to its electrons? So, let's first take the case of sodium, which sodium is element 11. It's 1s2, 1s2, 2s2, 2p6, 3s1. Now, if you notice, let me draw this. So many dots. 1, 2, 3, 4, 5, 6, 7, 8. Okay. It's got the little buddy hanging over here in 3s1. This 3s1 is going to be a really easy electron to remove because sodium only has it's got 11 protons. If we were to compare the alternate case of neon, which is 1s2, 2s2, 2p6, and although it has 10 less protons, removing this outer electron is going to be way easier than pulling one out of an entirely lower energy level. So if you have electrons hanging out in the higher energy levels, they're going to be easier to remove. That is why these elements over here always form cations and ionic bonds. These ones typically you see Na1+, Mg2+, lithium 1+. These ones lose their electrons real easily because they have those just 1 electron sitting on that energy level, even though they don't have that much more protons and quote-unquote pulling power. So let's take a look at another one where that's not the case. How about let's compare nitrogen and let's compare oxygen and fluorine. Okay. Let me write the configuration for these real quick. Fluorine is 1s2, 2s2, 2p5. Oxygen 1s2, 2s2, 2p4. So now we're in the case where we're removing an electron from the same energy level and same orbital. We're pulling one out of the 2p. So the last example I gave, you'd think they'd have the same energy, but fluorine has 9 protons. Once again, fluorine has 9 protons. Oxygen has only 8. Fluorine's holding on to its 5th electron in that 2p orbital a little bit harder than oxygen's holding on to its 4th. So therefore, fluorine would be harder to get out one of those electrons because it's once again, it's pulling on it harder. It's got a bigger nucleus. So fluorine would have a higher ionization energy, and then same thing as you go over here to the left on the periodic table, you decrease first ionization energy because those electrons are just out there sitting in higher energy levels. So what does the overall trend look like if I combine the two observations that we just saw? It trends, first ionization energy trends like this. Whereas, once again, if fluorine's the reference, fluorine has a really high first ionization energy. It's really hard to pull it off. Okay. Okay, let's talk about, erase everything again. I'm going to leave the dots. Okay. Electron affinity. Electron affinity, I'm not even going to give the formal definition of it, but it's essentially the same thing as electronegativity. Conceptually, it's similar. I'm not going to say the same thing. I don't want to get in trouble. It's similar to electronegativity, whereas it's more or less the ability of an electron to, or the ability of an atom to pull its electrons in. Very similar trends to what I just said. Whereas, let's see here. Let's compare, I guess I'll just go into examples. Let's compare, well, let's just do oxygen and fluorine again. Maybe I shouldn't have erased everything. Oxygen is 1s2, 2s2, 2p4. Fluorine, 1s2, 2s2, 2p5. With, let's see, this one has 9 protons, this one has 8. So which one will be able to pull onto its electrons harder? So which one will be able to pull on its outermost electrons harder? It will be fluorine because, once again, it has more protons. It will be able to hold on to these essentially better. And it's not the same thing as first ionization energy. The definition, I think, is a little unnecessary because it's a little confusing. But it follows a similar trend. And as we go down, here's another trend. So as we go down, so we know electron affinity and electronegativity increase this way because we have electrons in the same energy level, but we have more protons. Now let's consider the case where we go down columns. Let's compare fluorine to chlorine. Wow, this is really in my head now. The fluorine configuration. Okay, here we go. We have fluorine and chlorine's electron configuration. Which one's going to be able to pull onto its outer electrons better? Well, chlorine does have more protons. This one has 17 protons. This one has 9. But if we look at, once again, Coulomb's law, the force that it can hold on to those outer electrons is very proportional to how far it is away, and also how much those electrons are repulsing each other. So the chlorine will have its electrons out here, and it's not able to pull onto them as hard as fluorine will because they're so much farther away, and because these electrons are repulsing each other. So Moral of the story is, for reference, fluorine holds onto its electrons really tightly, and the trend looks like this for electron affinity, electronegativity, ionization energy. I guess that's the only ones we talked about. It looks like this. Fluorine's the high example, and then it decreases down and to the left. So that's the trend, and that's generally why. I think if you can remember kind of why, it makes it a lot easier to remember, because as you might have noticed there, it gets kind of repetitive, and if you know one, you know them all, more or less. I think memorizing this sort of quick explanation is better than just, oh, it trends that way or it trends this way, whatever. Anyways, I'm rambling. Okay, let's do the problems. Okay, so let's move into the problems now. 21. Which one of the following lists the correct order of increasing radius from smallest radius left to largest radius right? And they give us 5 choices. So let's find these choices on the periodic table. We got aluminum there, magnesium, sodium, and then what do we have? Fluorine and oxygen. Okay, those are our 5 elements. And I'm also noticing that these are in their ion form, which means they all have the same electron configuration. You can fact check this yourself, but all 5 of these elements have the same electron configuration, which I just drew there at the bottom. They all have the neon electron configuration. So if they have the same electron configuration, they have the same electrons, the electrons are not going to be the reason why the radiuses are different, obviously. So what's the only other difference between these 5 elements? It's the number of protons they have. And we know from that, I don't know what's going on there. We know from Coulomb's law earlier that, my pen seems to be freaking out a little bit. Okay, we know from Coulomb's law earlier that if you have more protons, you're going to have a stronger attractive charge, and it's going to pull things in harder. You're going to have a higher force. And if you're pulling things in harder, you're going to have a smaller radius. So, which one is the most protons and will be the smallest? Aluminum is going to be the smallest because it's the most protons. And then magnesium, and then sodium, and then fluorine, and then oxygen. So fluorine is going to be the biggest. It has the least number of protons. So it's pulling the weakest. So this looks like answer choice A. 38. Which one of the following is the largest radius? So unlike the previous problem, these ones do not all have the same electron configuration. So let's write out what these are going to be. Where's fluorine? Okay, where's 2p5, and then this one gains an electron, so 2p6. This one loses an electron, so 2p4, and then neon is just this. Okay. Well, when I look at answer choice B and D, they have the same electron configuration. So when we're comparing these two, they have the same electron configuration. But like the last problem, neon has more protons than fluorine. Therefore, it's going to be smaller. So D is not the choice. When we're looking at A, B, and C, they all have the same number of protons. So then the difference here is going to be the electrons. So they're all occupying the second energy level. Answer choice C only has 4 in that second energy level. Then we go to answer choice A. You're adding in a 5th electron. When we add in this 5th electron, there's going to be a little bit more repulsion between electrons. Right, electrons. Whoa, my pen is freaking out. Okay. They repulse each other a little bit, and it will actually make these electrons move a little bit farther away. As you add another electron into this, it will get a little bit bigger. So answer choice A is a little bit bigger than C. And same thing with B. If I were to add in a 6th, or well, actually, sorry, this should have 2 more in here from the S. But if I were to add in the 8th into that second energy level, it would get even bigger. So B is the correct choice. It is the most electrons there. And also, if you can imagine, I think a more hyperbolic example, if you can imagine fluorine 2 minus, that would have 1s2, 2s2, 2p6, and then 3s1. This adding this this outermost electron into the third energy level would make it way bigger. So if you can imagine adding a whole other electron and a whole other energy level, it would be way bigger. So I think that's kind of intuitive that as you keep adding electrons, you're going to get bigger. 38b. 22. Which one of the following elements has the largest first ionization energy? And then they give us some elements. So let's find these. Boron, nitrogen, phosphorus, carbon, and silicon. Okay. Well, let's first compare nitrogen and phosphorus. I'm going to do these two to make the first example. Nitrogen electron configuration is 1s2, 2s2, 2p3, and phosphorus somewhat similar. Wait, oops. 2p6, 3s2, 3p3. Now, these. Okay. Let me write Coulomb's law again. F equals some constant times the magnitude of the charges divided by the radius squared. Okay. When we're talking about first ionization energy, we're talking about how much energy it's going to take to remove the outermost electron, which in our case is either, for nitrogen, is an electron in the 2p orbital, or for phosphorus's case, an electron in a 3p orbital. Now, as we move farther away, as we increase our radius, you will have significantly less force pulling on the electrons, which will make it much easier to take away. Therefore, an electron that's farther away, aka in the 3p orbital, will be way easier to remove. It will have a much lower first ionization energy. So, phosphorus, and by extension, for the exact same reasons, silicon have lower first ionization energies. So it's not those two. Okay, so if it's not those two, let's compare now boron, carbon, and nitrogen. Let me write the configuration for carbon. 1s2, 2s2, 2p2. So now we're pulling electrons now from that same 2p orbital. So that is not going to be the reason for our change. Instead, here we should look at the strength of the nucleus. And nitrogen has 1 more proton than carbon and 2 more than boron. So it will have a significantly greater magnitude of charge, it will have a greater force, and it will be harder to pull away nitrogen's outermost electrons. It'll be harder than carbon and boron. So, therefore, 22b, nitrogen is going to have the largest first ionization energy. 23, the successive ionization energies for a certain element are. Okay, and then for the first electron, we have 578, and then down to the second electron, we have a massive jump. We have a huge jump in energy, and then from 2 to 3, it's pretty much the same. When those are the same, those tell me those are probably in the same orbital, because they're similar energies to remove. From 3 to 4, there's another massive jump, and then 4 to 5 are pretty much the same. So I think the first takeaway piece of information here is that 2 and 3 are probably in the same orbital, but there's only 2 electrons in this orbital. Because I know there's a jump before, and there's a jump after, right? Because 4 and 5 probably aren't in the same, and then 1's probably not in the same. So I know that this has to correspond to a s orbital with 2 electrons. And whatever is above this to the right, you know, like as I'm drawing my electron configuration, this is going to correspond to what's on the right. This could be 1 electron. Well, let me write it in green. This could be 1 electron in the D. It could be it also could be 1 in the P. I believe those are 2 scenarios. Yeah. And then these could be anything. Most likely, I'm gonna say this is the most likely scenario. It could be something like this. Where this is sort of the last. These are the electrons that correspond to these electrons we see above. Now, and if it was P, it could be the same thing. Something like that. Now, I didn't write in the energy levels because it could really be anything in theory. So, the main candidate that's coming to mind, I'm thinking of these 2 and these 4 because they have that 1 electron in the P or D orbitals. So, what do those look like? What is the electron configuration for aluminum? Just to maybe help make this a little bit better. Aluminum's electron configuration is 1s2, 2s2, what is it, 2p6, 3s2, that's a 2, 3p1. So then, yeah, this kind of maps to what I was writing here. These three would correspond to like the three we see there. If I think it would do the same thing if you wanted to map those four. Also, maybe boron. You could also do boron, which would be 1s2, 2s2, 2p1. So I suppose you could also do boron on top of the other four metals. These two could correspond to this 1s. But here the main takeaway is that you need to recognize that these two are in a distinct orbital, and there's only two of them, which means it has to be s. And that there's one above them, which means it's got to be like one in the d or one in the p. So that's kind of how you backwards logic your way to the correct answer here. So I'm looking for boron, aluminum, or one of these metals, which I have a hunch it's not. And yeah, we have aluminum. It's our only choice. 23D. 29. Electron affinity values for phosphorus, sulfur, and chlorine are listed below. Which one of the following statements best explains the trend in electron affinity values? These three elements are right here. They have 15, 16, 17 atomic numbers, respectively. 15 protons, 16 protons, 17 protons. Okay. And they want to know what explains the trend. Answer choice A, the effective nuclear charges increases across a period. That's true. So we know from what we just looked at, this is how they're arranged. And as we go across a period, aka go this way, chlorine has a greater number of protons, which means it has a greater effective nuclear charge. So that's true. B, the effective nuclear charge decreases across a period. It's the exact opposite. C, the principal quantum number, n of the outer electron, increases across a period. This is not true in this case because, let me write out the electron configurations. Let me do this quickly. What is this, 3p3? And then, I'm not going to write this whole thing. I'm just going to skip 3p4, 3p5. This is all the same. If we look at the outer electrons, which are these, they're all in the same principal quantum number n, which is just the energy level. They're on the third energy level. Not true. D says the exact same thing with the opposite. D, not true. 29A.